the Hadoop infrastructure, and I have to record. Good. I think that someone is recording, so it's fine. The Hadoop infrastructure is an Apache infrastructure. It's an environment that is composed of several tools that are able to run operations under the MapReduce model and on clusters, okay, in a parallel manner. Even if, as we saw in the regular course, parallelism is a little bit hidden because this is the principle of the environment. Let us, of course, reason more or less about parallel issues, resources, but not really getting into the complex burden of really doing parallel programming. Okay, and this is to democratize parallel programming, in fact. So anyone that is able to program and is able to design MapReduce based algorithms can run parallel processing tasks without more difficulty than that. Okay. So the infrastructure is composed so that you have the general overview. So it's composed of the following architecture. So of course, it relies on clusters that provide particularly processing and storage support. And the clusters are organized as a coordinator worker setting. Okay, so if we concentrate on data, what we will see is a set of storage of disks that we have available, and that for which we will have the view of their content through a distributed file system. Okay, so even if data is distributed somewhere in some disk, we have a global vision of the content of these several portions, and we have classic associated operations in order to look up files and then to retrieve files. And so this is the role of the HDFS. I remind you that HDFS is the acronym of Hadoop Distributed File System, and which is the open source version of the Google GDFS, Google Distributed File System. So this is the underlying generic storage support that provides management of data to the data processing infrastructure. Of course, here it is possible, as we will do today, to have other options, okay? As long as they provide us access to the data we need in order to run our programs. Then we have what we're going to use today, an engine that is able to run MapReduce defined programs, which means that it is able to deploy on different CPUs, on different servers, the execution of the mappers that run the map function, the management of the intermediate results, and then it triggers the set of processes that implement, a set of reducer processes that implement the reduce function, and it interacts with the HDFS that serves as common memory for all the processes that run a program. We can have this, well, then a question comes with regards to how are we going to feed data here, okay? And so the Apache environment provides tools in order to do the ETL process in batch, as we all know how to do it, like putting data offline into the file system, or collect data continuously for streams. Okay, so it provides these cartridges that can interact to EFS when data are produced continuously and they are stored in this distributed file system. Then we can also have, well, this is a file system. We all know the file system. I mean, the most complex operation that we can do is look up, but the complexity of our search operations is not evolved because it is a kernel very close to the disks. So there is no further infrastructure that we can use in order to explore the content stored in the data. So it is possible to associate NoSQL systems, okay, in order to have a less primitive way of accessing data stored in a cluster. And so an example is HBase, but you can have Mongo, you can have Neo4j or whatever you need here. The Apache environment uses HBase, but it is possible to use other solutions. So it is identified, I mean, it is located at the same level of MapReduce because, I mean, both of them rely on this HDFS support. And here, as well as here, we can perform queries in parallel. Okay, when we define a program, we are defining, in fact, a query. The difference is that the query is expressed in an imperative manner, whereas normally in NoSQL systems, there is at least some primitive or some primitive operations that are already built in and for which we do not know the implementation, but we can use them in order to query the data, as we have seen in Mongo, for example, or in Neo4j. So anyway, here this is required. And of course, since you know relational databases, any data management system in its interior relies on file systems in order to deal with the data and retrieve the data and work with it. So this is the classic internal architecture of data management support. The difference is that in the Apache environment, everything is exposed. And in, for example, in relational, everything is hidden within the data management system, which is best, but it depends on our technical capacities and on expected time to market. Here, this is nice, but this requires a lot of technical knowledge, whereas in the other solutions, you require less technical knowledge. Anyway. And then there are associated services that compose this environment. First of all, here, even if it is not exposed, I have insisted a lot on the fact that we are working on a cluster of machines. And when you deal with a cluster, you need to monitor the use of the nodes of your cluster. You want to know which one is most busy, whether all are available all the time, who has connection problems, etc. So this monitoring of resources, of course, you want to monitor main memory because if main memory is exhausted, then you will have problems to run your programs. You should also be aware of the available resources so that you can make decisions on the resources that you are going to allocate in order the processes to be run. Okay, so this kind of management is done by hand and is done by a programmer. Okay, so it's done by you in the second phase of the use of Hadoop. Okay, so for this, this environment provides this service called Zookeeper that has all the necessary libraries so that someone can monitor the use of resources within a cluster. And then here at the top level of the architecture, so programming in MapReduce is cool, it can be interesting, but everyone knows that programming implies a lot of, well, first of all, writing the programs, but then managing the code, debugging problems when they appear, and of course, you will see that the execution is quite obscure, so the debugging process can be a burden. Okay, so and this costs time, and if you are providing a real solution, well, you don't want your programmers to lose time in this kind of tasks. And also program maintenance is also an element that, and program testing are both tasks that are two tasks that have to be introduced in the production line of the solutions, and so it takes resources. The Apache environment provides high-level services that help people, instead of really programming in an imperative mode, have a SQL-like expressions or declarative expressions. Most of them are inspired in SQL, because we are dealing with data, to do many things, okay? So for example, to do exploration with many built-in operations that help you express easily your data processing and exploration operations without having to implement them. And then, for example, Hive, which is a multi-dimensional cartridge to do aggregations, etc. As you have learned in data warehouses, but here without the DBMS, with columnar solutions most of the time, and then you can define your similar to OLAP operations that can be used in order to do aggregations and do analytic in terms of aggregated data, more or less easy. So this is Hive, and Choka is more or less the same, also for analytics and also declarative. Okay, so this is the general overview of the Hadoop environment. It is important that you can identify which are the elements that we are studying in the course, which those that are not, but that you bear in mind what their purpose is, and that you know the general environment, that you are, can show that you are acquainted with this Hadoop environment. Right, so now how does it work? Well, it works, we will see in some minutes. It works in a very pragmatic way. Okay, so you have written your count words, you have written your map function, your reduce function, and then you are going to run. And the first thing that you have to do is you are going to submit a job. This is the vocabulary of this context. So your program, as you all know, when you run a program, it becomes a process. And from the eyes of the Hadoop environment, it is a job to be executed. So you are going to submit your job to the master of your cluster. This you have seen in the Mongo sharding exercise. So we have this entry point towards the cluster, and it was there where we entered the cluster and started operating. So in the query router, well, before the entrance and then the query router, okay? So you have more or less the same. You have this entry point, which is the master of your cluster, and you are going to submit your job on top of it, okay? And the master of a Hadoop cluster is called the job tracker. Okay, so here you have the job tracker. And then you're happy because the infrastructure itself is going to deploy instances of your program. So it's going to divide your program into subjobs, which is a mat function, and it is going to deploy these instances, deploy them on the different nodes of the cluster. How many nodes, etc. This has been configured in a previous moment. Okay, so under a pre-configured version, I mean infrastructure installation of Hadoop, it will decide how many mappers it will run on the different clusters, and so it triggers that. So then, since this has been pre-configured, so you do not have, as a programmer, to say, go use this node, and this node in order to execute my sub-instances of the program. It will do it automatically. And then it will also care about the synchronization. Of course, if you are running different processes on different nodes, they run in an asynchronous manner. So depending on the occupation of your different nodes, your processes will start and will terminate at different moments. And the infrastructure will be observing these executions, and when everyone has finished executing, it will know, okay? And then it will decide to do shuffling and sorting and shuffling, and then triggering the next step, which is the a set of reducer processes. Okay, but this is the job of the Hadoop infrastructure when we are using Hadoop. So distribution, synchronization, and failure are handled by the system. So if for some reason your process cannot terminate in one node, the job tracker will observe this situation, and it will deploy your process in another node, and it will decide, depending on the way it has been configured, whether it keeps the state in which before the fault, and then it continues with the rest, or it starts the process from the beginning. Again, this wonderful decision is by the infrastructure. Have you used peer-to-peer systems with torrents? Okay, so I don't know what you use. I use mu. Okay, so what happens when we see something that we are interested in? So we choose the file that we are interested in, and then you have seeds. The seeds would be the different nodes available for retrieving a file. Okay, and what is wonderful about the solution is that seeds start providing pieces of the whole file. You do remember, don't tell me that you do not access to stream films or music or whatever. I will be very surprised about that. But well, it's not officially that you have to say it, but I suppose that since you are people of this era, you have had the experience. So anyway, so you all the peers start providing pieces of the file that we are interested in. So let's say that we are interested in getting Batman's last film. So all the seats that have this film will start providing pieces of the files. And if one seat goes away because I didn't want, I closed my computer and then I decide without caring about anything, the system will make sure that the retrieval of the file continues in a certain point, okay? So without, and even us, if we close the computer and then we open it again, the system will keep in the last state in which the file stopped being retrieved and composed, and it continues, and it doesn't start from zero, it continues where you stopped and until the file is completed. Okay, so this is, and we do not care about this. We do not care of how many seats are available, whether the seats are going or not, and whether and at which point of the file retrieval we are. This is done by the system. Well, it's the same principle, but here we are not retrieving data, we are processing data, okay? But it's the same, we send our job, and then it is up to the infrastructure to decide how to deal with the different peers, with the different nodes, because here it's a coordinator worker setting. It sees how it goes, and then it moves the processes from one node to another if there were problems, etc., until the whole process is terminated. Okay, so this is the principle of the execution. Here is the description of what I described orally in the figure. Okay, so I'm not going to go through it because I have already said it, but if you didn't catch all the blah blah of the description, you have it here in this slide. And so the architecture looks like as follows. So I'm going to first concentrate with one coordinator, okay? So you have your coordinator, and if you remember well, we have like two moments of the process. First of all is the moment in which we are here, okay? First of all, we have to see what happens here, and then we can see how this management of the data interact with the MapReduce engine in order to execute our operations, right? So this I had already described in a previous session. It's just a reminder. So we have a coordinator workers infrastructure. The workers are full-fledged machines, which means that you have a file system, you have one or several CPUs, and you have a disk. Okay, so you have your complete architecture, and on top of it you will have data node. So this will be considered a node, and so you have a daemon that is observing what is going on with respect to the files inside the server. And then you have a task tracker. The task tracker will be observing all the processes that are running on concerning the whole infrastructure that are running on the server. Okay. Normally, servers, these are dedicated servers. Okay, so the only possibility to access them is through the coordinator. Okay, there are never accesses like this. Okay, normally in these settings. Okay, for example, in the peer-to-peer solution, it's not the case. So it's a more difficult thing to manage. But here, the only entry point assumed is the coordination node daemon, and then the rest of the system. And then, as you remember, the name node will have a daemon, and then this daemon will interact with the little daemons that are running in the different participants of the cluster, and they will interact within among each other in order to deal with the data. So this is the file system, and together with this, in the you have another node, which is the one that deals with your MapReduce execution. So, and this node is called the master or the coordinator node, and it has a very important process, which is the job tracker. And the job tracker will interact with these task trackers in order to observe the execution of the processes. Okay, so our program will come here. We are going to submit our job here, and it will be up to the job tracker to deploy it on the different workers and interact with the workers in order to execute the program. And of course, beforehand, we assume that the pieces of data that are required in order to run each of the processes has been already deployed on the different nodes. So you prepare your data, you distribute it in across the cluster. This is done using the distributed file system, and then everyone is there, and then you run your program, and so the program is already has already the right functions in order to upload the data into main memory required for processing, and then it runs, and this is observed. So it's basic execution, as we have learned in, I mean, during the whole career, but now the only difference is that you have a synchronization problem that is solved by the job track. And of course, on top of a different architecture. Do you have questions until here? I suppose that you are amazed with this, because this is computing systems in its pure state. This is our job. Okay, this is what we have been working for, to do this. It's wonderful. I find it wonderful. So more or less. Now, of course, for pedagogic reasons, it is possible to start step by step, as we are going to do, because otherwise it becomes a little bit complex. So I want you to learn, not to overwhelm you with a huge bunch of information. So for example, today we are going to run on just one node. Okay, so we will have, of course, two processes, the coordinator and the workers, but we will only have one node on top of which we are going to run this. And then afterwards, we will have a cluster and then run it on a cluster mode, which is also very interesting of these kind of solutions, because even if for the time being you do not have a cluster, you can test on one machine, simulating the interaction of coordinator workers' processes, and then you can scale to more and more and more and more servers, and this is done in a more or less smoothly manner. Right?
Did you have a question?
Let's continue. Here we have some details about the task tracker. So about this little process that is installed in the nodes. Yes, please.
Yes, and the coordinator in this case is the job tracker.
The coordinator for the execution is the job tracker. But for the file system is the name node.
File system is the name. Oh,
You
okay, I
see,
see.
you have like here. So you have this complex thing which has a coordinator and workers. These are all disks, no? Processes accessing to disk. And here you have the name node and the workers of the HDFS. And this corresponds to this. You have your name node and you have data nodes. Okay.
Oh, okay, I see. Thank you.
Right?
Yes.
You see, and then you have the job tracker and your task trackers. So the data node daemons are the workers of the name node daemon. And the task trackers are the workers of the job tracker.
Oh, okay. Yeah.
Right?
Yes, yes, yes. Thank you, teacher.
You're welcome. Okay, so what does a task tracker do? Well, you have your program and it becomes a job, and the task tracker and the job tracker uh, in, deploys your process on the different task trackers. So a task tracker will accept the following tasks: a map, a reduce, and a shuffle and sort. Okay? And this by interacting with the job tracker. So the job tracker is the one that has the global picture of the execution. So it's the coordinator. Okay, so it first says, okay, I'm going to start executing mappers for the map functions. So it contacts the different trackers. The trackers receive the job and execute what it's required. Then they say, okay, I have finished. So they send a message to the job tracker saying that they are finished or that there was a problem. Okay. And then, well, each task tracker has a number of slots for the tasks. Okay. What you have to consider is that these little nodes with servers, in fact, are composed of several CPUs. Okay, so you have racks of CPUs installed in every node. So the idea is that the task tracker must decide to which part of the which machine, which CPU of the rack it is going to deploy the job. Okay, for example, a mapper, a reducer, or whatever. Okay, so it's not like a dull thing that it just executes, since it has several CPUs, so it decides where to put the job that arrives from the job track. This means that, for example, in the case of Java, for example, all the CPUs have a Java virtual machine, for example. Okay, so everything is really prepared so that the jobs can be deployed and can run. And it also indicates the number of available slots to the job tracker, because the job tracker is seeking for a balanced distribution of jobs. Okay, so by heartbeats, the task tracker will inform about the status of the whole execution environment that it manages, such that the job tracker can decide for some, if a task tracker is too busy, if a node is too busy, not to deploy some job into that task tracker in order to avoid problems, okay? And in order to ensure a balanced distribution of the jobs. So it looks very much the same as the reasoning that we have done for the sharding with Mongo, but in the sharding with Mongo, it was an even distribution of the data. And here, it's an even distribution of the processes such that the computing resources are balanced busy, no? So that in the whole system. So questions until here? I think that, I mean, intuitively, it can be yes. Please, Maurice.
Yes, I have a question in the last
Yes.
thing you said. So this is uneven. I didn't understand why it is uneven.
No, it's evenly.
Even.
It
Ah,
should
okay.
be evenly distributed.
Yes.
So if you are a job tracker, you are your objective in life is to that the whole cluster is balanced in terms of a number of tasks to execute. That's your objective in life as a job tracker.
Ah, okay. Thank
Yeah.
you.
Other questions? Okay, so let's continue. So us as programmers, what do we have to consider? Well, the idea is that, even if it looks a little bit complex, it's that many things are simplified. Of course, here we are opening the box and we are trying to see how the internal processes are done, okay? But normally we do not see that, and it is transparent to us. So the idea is to simplify as much as possible the execution of our programs. So it takes care of the preparation of the input data, and the programmer only has to program a mapper, a reducer, and optionally add combiners and partitioners in order to optimize the implementation of his or her program. Okay, so that's the only thing that we have to deal with. So the type of exercise that we did in the regular course, that's what we need. We need to think about our data structures, about the way we are going to implement our map function, our reduce function, but nothing else, okay? then an important thing to consider is that any conceivable algorithm that a programmer wishes to develop must be expressed in terms of small, rigidly defined components that must fit together in specific ways. So that's the challenge. I mean, if we were thinking of this as a game, the complexity of the game is that we only have two functions, that we only have one data structure possible, and with this, we must implement anything we want. Okay? So that's the challenge of the game. If we get through this, then we are over, because the rest will be taken care by the infrastructure. So synchronization is maybe the most tricky thing to consider when designing a MapReduce function, because we have to make sure that the way we program solutions really contribute to the execution, the smooth execution of the map and the reduce function. So anything that deals with references, with something strange, will create overhead. And overhead in parallel programming is very penalizing, and we are not seeking for that. Okay, so the tricky part is really the way we design our solutions. So the blocking element of these kind of solutions is the programmer and not the infrastructure. Now, what is beyond the control of programmers? So once you are acquainted with the model, once you get experience in programming under this model, then beyond your control is where a mapper and reducer runs. Okay, so this is up to the infrastructure to consider according to the cluster you provide. When a mapper or a reducer begins or finishes, this is also up to the infrastructure to deal with. Which input key value pairs are processed by a specific mapper, the same. So the allocation of the fragments of the data is decided by the infrastructure, and which intermediate key value pairs are processed by a specific reducer, the same. So you have your partial result from coming out from the mappers, and then it is up to the infrastructure to reorganize them, etc., deploy them on the different nodes of your cluster, and then start the reducer processes. Okay, so that's something done by the infrastructure, which is not the case when you program in parallel with other solutions. So under your control as programmers is, as I said, the famous data structures. We never get rid of that. Okay, so our destiny is think about data structures. The way data is initialized, so the ETL, this transformation process, is also under our responsibility. So the fact that we have to consider that mappers and reducers should only have one input, okay? So nothing else, otherwise penalizing. Then the shuffle and the sort and shuffle parts are already built in and implemented within the infrastructure. But if in an advanced setting, it is possible to change, for example, the algorithm used to sort the data and to shuffle the data. This can be done by modifying the backend of the system. And this, if we want to do that, this is up to us to do that. And then the ability to control the partitioning of the key space. Okay, so of course, during the design process of our data structures, they shouldn't be naive. In fact, they should really consider how to organize the data and model the data in the best conditions such that the whole process will run smoothly and with less overhead possible. Okay, so in a professional design exercise of our algorithms, this is something that people should care about. Of course, us will get to the beginners part. Okay, we will not have time to go into a professional use of this kind of environment. So the important that you have to bear in mind is that, I mean, the regular design process of your data structure, and then the implementation of your MapReduce functions, and that's it. And whether what does it imply in the shuffle and sort states, intermediate state, to have a specific data structure as output or as input for the reducer, but that's it. We will not get into advanced aspects of the configuration of the environment. But it's important that you know that. Okay, so let's put things into the matter. So before we start, do you have questions? So you are at the end of your career, and suddenly you are discovering that there is a lot to be learned still. But this is normal. So in order to go to the hands-in, yeah, I mean, that's normal, and it's important that eventually for preparing your professional career, you take that into consideration in order to organize this professional life. So I'm going to share the link to the specification of the exercise. So I'm going to start sharing. Well, no, I'm not going to start sharing this. So let me put this in the chat. So here you have the specification of the exercise. No, this is not what I'm looking for. This is what I'm. So just what I explained to you. I don't know if we get to see. Yes, we will. This one is very simple. So if you go to the address that I provided in the on the chat, so we are going to do first steps on Hadoop environment. Okay, so the first exercise will show, of course, how to install it in an externalized setting, and we are going to use our Colab environment. I think that next time, depending on how far we get, we are going to go back to Azure and really have a cluster, etc., and have another kind of setting. But for just to do our first steps today, we are going to use Colab, and then observe how to implement and run the MapReduce program. Okay, that it's provided, so you do not have to run it, and you have guessed the one that we are executing is the Counting Words. So what we need is a Google Colab account that you already have, and the exercise lies here. Okay, so when you get to my GitHub, you click on opening Colab, and then you will land to a Colab node. So bear in mind that the steps of the exercise are completely simple. We are not running on a cluster. We are just going to use the CPU allocated by default by the Google Cloud, because this will help us first to concentrate on the way we deal with these MapReduce functions. Okay, how do we program them, where do they lie, etc. And then as I said, we will do other things later on. Now, to do and to hand in. Okay, so you already have an assignment on Blackboard. Okay, so you have to propose an UML component diagram of the Hadoop environment that we installed on Colab. You will see that throughout the lab and throughout the regular course, I will insist a lot on that you acquire the experience, and there I hope that you acquire the advanced experience of being able to specify your environment, work environment architecture, and that you make the difference between this environment and what you implement. I have the impression that for the time being, you have a tendency not to see these two elements as separate elements. They are always like together in your minds, at least from what I have seen in your work. So it is important that you make the difference and that you are absolutely able to specify both elements using UML. Okay, so first thing will be how the Hadoop environment installed in Colab looks like in terms of components. Then, again, another separate UML component diagram of the two MapReduce CountWorks programs tested in the lab. So that concerns the program itself at runtime, which are the processes that are interacting among each other in order to run the program. So that's a second UML. Then you have to explain how the first example in the exercise I will show you in a second. There are two exercises. One that tests the after installation, it provides a test to make sure that everything has been correctly installed, and it implements a grep operation using a regular expression. So you have to explain how this example works, and then explain how the program CountWorks is executed in the second example, and what is the role of Google Drive in both examples. Okay? So this is a report where you provide all these. Now, when you draw your component UML diagrams, again, many of you have the reflex of saying UML diagram, but of what? Of a refrigerator, of my elliptical machine, or your computer, or what? What are you representing? So you have to say, this is a component UML diagram of the work environment, or using Hadoop on Colab. Okay? It should be explicit, otherwise it doesn't make sense. And so that's one thing. And the other thing, make sure that your UML diagrams adhere to the specification of UML. So components should be named. The arrows have a meaning. They have to be tagged. So respect the specification. Okay, here we are asking for components. Some of you, for example, in your work provided class diagrams without attributes. This is not acceptable at all. Okay, so please be rigorous in the use and the specification of your diagrams. Okay, so if you already clicked on the line to something like this. So are you lost, or do you know what? So if you clicked on the GitHub, you landed here on my GitHub. And then you can open in Colab, and if you do that, you will open in Colab like this. Is everyone on the same page?
Yes.
Yes.
Right. Okay. So as I said, well, I'm going to display this. Okay. First of all, what we are going to do is we are going to install Hadoop, okay, on our environment. So the version we are going to use is 3.3.0. So we are getting it from the Apache or so the right provider. Okay, so you can run. Let's see, LLM. So we got a JZ tab, and then we are going to untap, and we see what happens. So when we untar the Hadoop engine, we will end up with Hadoop, the engine, and with a set of sample data provided in order to test. Okay. So first test will be done in Java. So in order to do that, we have to configure the path, the Java home path. So this we are going to do here. So when we do these simple things now, you are figuring out Google Cloud, your Google Drive, the Colab service, and then where the CPU provided by the Colab service, and then what are we doing when we, for example, downloaded the Hadoop, and what are we doing when we are setting the path of the Java home. Okay? So of course, I'm just lighting the different elements. The idea for the exercise is that you reason about it and do component type. So we have our Java home set. Now what we are going to do is, well, we are going to get rid of the sample data, okay, because we are not going to use. But this is just a fancy thing because I am controlling this. Okay, so, but this is extra, okay? This is because I didn't want to keep the sample folder there, but it's just that I'm sparing the space of my drive. So now we are going to run the engine. So remember that if I'm running the engine, what I'm running is something, an environment that is able to have a coordinator, the one that will control the execution of my MapReduce processes, and that will interact with the file system in order to deal with the intermediate results and then with the final results. So this whole complex machine of the job tracker, the task trackers, etc., is there. Okay, so that's what we are running now, and that it's running, of course, in in the CPU that we have allocated. So it does a lot of things, and particularly what it does, it connects the engine to the file system, because they are a dynamic duo that will work together in order to run our programs. Okay? So that's what it's doing, and since the file system pre-existed and the engine is just running now, it establishes the connection with it. And that's it. So as I said, I promised that it was obscure, and I'm keeping my promise. So the first thing that we are going to do is do a test to know that now the Hadoop is running, but that it's really running and that it works. Okay. So what we are going to do is, first of all, it's a word count, okay? So we are going to configure access to the input files. So here, everything is done by hand, okay? So we are creating an input one directory. We are going to this directory, and then we are having a look at the content. So, we copy the input on the space, and then we see the input. So that's what we are doing here. So of course it does a lot of things. Yarn is a virtual environment that hosts all the engine and all the apparatus of the engine. We will go through Yarn later on. Here, the only thing that you have to consider is that the engine runs in a container, in a kind of container, generally speaking. There it has all the components necessary to run, and this container is called Yarn. Okay. It also has an HDFS environment, and it has an scheduler that deals with the jobs. There is also an XML, various XMLs that specify the resources, I mean, the configuration of the environment, the size of main memory that we allocate, the number of jobs that a node can execute, etc. So all the configuration in terms of resources of our environment are given here. As you can see, for the time being, we can keep as such, but eventually in an advanced setting, we as administrators of a Hadoop cluster could move this. To make the parallel so that you have some reference, for example, in the sharding exercise, the allocated memory of the chunks was predefined by the Mongo cluster. We could also extend this allocated space. Okay? So instead of having 256 of space, we could have said, now I want 5K something megabytes or whatever allocated to my spaces according to the capacity of my nodes. Okay? So this is contained here. So we have this, and now, so as I explained in the oral presentation, first thing that we have to do is allocate the data. Okay. And so this was done well in a very simple manner here. Okay, so we allocated the input data that we were going to use in this address. Okay. So that's what we did. And now that the data is allocated in the right address, we can count, for example, the number of times that this expression appears in the input that we provide. Okay, so if, later on, if you are curious, you can go here and explore in this address the head of the input. Okay, it's a file, a text file. Okay, so what we are doing is we are saying that we are going to execute MapReduce lying on this examples component in order to count the number of times that this regular expression appears in that file. Okay. So have a look. This is it. So it runs a lot of things. Let me go to the top of the so that I can explain. So a very simple thing, and have a look at how many things are done. Yes. So it builds a path, it creates comments. No, this is not what I was looking for. So you have your job tracker, and it is started in order to start observing the system. Okay, so it received from the as input 10 files. These 10 files were split into 10 portions. No, in fact, it receives one file and it is split into 10 portions. That's what it means. And then it creates a job. Of course, a job with an identifier. Then the job to be tracked is accessible in this port. Now it is running the job. It runs a job and it's waiting for the map tasks to be executed. There are attempts of execution and of interaction with these processes. What else? Well, here we have, for example, all the characteristics of the resources allocated in the processes. Okay, so the buffer at the beginning has 0 elements. Then it increases the number of elements. There is the collector class. Okay, you can imagine that you have a map, a process running the map function. When it gets the input from the file system, it is allocated in main memory. The process starts, and at some point, someone has to collect the results, intermediate results of the execution of this map function. This is responsibility of a class called a collector class. Then, once it has terminated, it flushes the output of the execution of the maps. Then there are other attempts in order to execute the other jobs. What else? Well, here is the statistics of the of the number of bytes used, read, etc. And then here you have the statistics of the resources used in order to execute our program. So it continues, etc. And at some point, so you see here, for example, these are all the interactions that are done between the job tracker and the local task trackers. Okay. Then here you have information about the interaction of the process with the file system. And then it continues, and then it interacts with the file system. Then again, it provides you statistics of the execution within the framework, and so on and so forth. Okay, so you see, we are just executing counting words. So if someone had seen us at the last semester of computing systems engineering programming this very simple program, they would have laughed. No, if your parents, if they are not computing scientists, see what we are doing, they will be very angry. Because after so many years of engineering, I'm asking you to count words. Very simple thing. Well, this simple thing deployed on this kind of an infrastructure becomes that complicated, because it's not about the difficulty of the algorithm itself within the map and the reduce. It is about the synchronization of a set of processes that will be running on top of different machines, and then collecting the data, and then starting other processes in order to obtain a result. And this is intended to go faster than if the same program was executed in a normal way, okay, on a Java operation, Java program running on your PC. Okay. So I will now go into further details of the technical aspects. So you have understood that this is back and forth until all the mappers, all the reducers have finished. And then what is the result? The only thing that we are happy about with all this feedback is that there were no errors and that the execution ended successfully. Where are results lying? What else? Where are they lying?
Can you repeat the question, please?
Yes, where are the results lying? Until here, we know that there were no errors, that our program, the map and the reduce, were executed and were executed successfully. But where are the results? So remember that the result is we wanted to count the number of times that the regular expression provided on the top of the here. How many times did it appear in the input file? Yes.
I believe there's a log that says final counters for attempt, and then it says the ID of the attempt counters, and it says how much.
But where is the result? The result, I want to count the number of times allowed when this expression appears in the files. So I'm expecting a number, no, of times. Where is it? It's not in the log. The log is the log. The log just provides me with a lot of feedback of the conditions in which my program was run. And this is important. Well, if it's successful, it's not that important. But if there is an error, then it's important because I have to go through the log and see what was the problem. Okay. the log is also important because if I want to change the allocation of resources, then I will be able to compare. If I provide much more main memory or more CPUs or CPUs, more powerful CPUs, etc., then I can have a look and compare. But the result itself, no cues?
Like Jose Antonio was saying, I think in the output directory.
Yes, in the file system. Okay, the only way of pulling results, pulling data to feed a program is the file system. And the only way where we can have a look at results is by pulling results from the file system. Okay? And this is why we are doing this. So excellent, because now I've lost something, but well, in this address, you will have something, let's see, yes. Something went wrong in my execution. I don't have time to
I
see
think it's
that.
because the directory is output one, not just
Yes,
output.
it's right. So here you have to modify. I let you modify so that with the right path. Yeah. Well, if you modify with the right path and you have a look at this, there you have the result. You see, so as I said, I mean, it's not obscure in itself. We are computing engineers, so we are used to interact with terminal and with files in a non-graphic manner. But this is also intended to say that now we are really going into a field of programming that is less friendly, if you want, with respect to what it is possible to see by running programs in normal, I mean, in PC or personal computer conditions. Okay, so that's something that that we have to bear in mind. Yes, Alexander. It's
Thank you. I wanted to ask in what format these output files are. I
in
cannot see the
text.
extensions.
In
In
ASCII.
text?
Yes.
Oh, okay. Thank you.
Mm-hmm. Yeah, it's the most, it's as if we were going back to you. This is why I insist a lot. So the first, if you remember, the first thing you started programming, the data were very simple. They were text, they were number, integers. So this is again the case. The problem is that out of this initial simple data, we have to build our key value structures and then again put them into the output. But the output is a record, key value record. Very simple thing. And then of course, if we want to go further and have other more complex settings, this is adding layers in our solution. This would be the kernel of a solution, and then here you can build a very complex system, I mean, a classic one. For example, you can take service as a software, you know. Dropbox is a distributed file system. And normally what they provide is an application where we see a graphic version of the file system. It hides the distribution of the data, the clusters, etc. We just see a generic view of the data that are lying in data centers somewhere in the world. But this is, so if you are Dropbox behind and they work with HDFS, okay? So they would be working in this kind of of pedestrian setting, and then the rest is built just for final users to be comfortable interacting with the system. So what you are going to do for next time, this was run in Java, but the second part of the exercise and the purpose of the first exercise was only to test Hadoop, okay, to make sure that we installed it, that the engine was running, and that it was possible to run something. Okay, that was the first part. Now, the second example is given in Python, and there, when you will go through it, you will see that we are going to observe what is contained in the map function, in the reduce function, etc., so that you can have a more complete vision of the way we do things in order to us program something. And well, I will let you do it on your own. But next Tuesday, we will discuss very briefly what you observed. And then, as I said, we will go to a more complex setting with a cluster, etc., so that you can see how it looks like to have to prepare a cluster, to have a look at the different elements that intervene in the infrastructure. Do you have questions until here? Are you excited? Or is it too weird? You can say that it's weird. It's not I will try to make sure that at the end of the part that we are addressing with map reviews, that it's less weird. It's just that it's interesting to have your feedback. So is it weird or not? Complex. It looks complex, yes. It looks obscure, no? Rather than or is it complex too? Yes. Right. You're curious. Good. Ah, it's applications. It's just that we want to run fast programs. The only purpose of a map reduce setting is that we have costly algorithms. Well, the count words is not costly. This is just a pedagogic exercise. But in general, the idea is that there are complex algorithms, particularly those NP-something, these kind of families, or algorithms, for example, in artificial intelligence that are greedy in terms of computing resources. So if you have a huge set of data, they can run for days. The idea is that instead of those algorithms running in days, try to figure out whether you reduce the execution time. That's the only purpose of this. And since, well, now if you connect with this idea of big data in terms of volume, now you are making it possible to run greedy algorithms on top of huge amounts of data. This is what it is.
Awesome. Very well. Thank you very much, Doctor.
Mm-hmm. You know, for example, now in the pandemics, all the decision making of the governments and understanding how to, you know, restrictions and how the virus was being distributed. Normally, algorithms run on graphs, and these were very costly. So, in the previous pandemic, in H1N1, they started using parallel solutions, and they could predict the way the virus was spreading in hours. And this was important because in that way governments could decide what to do or etc. So this is the use of this. I'm not sure. I will try to figure out whether that is possible in the conditions that I'm not in the university, but I wanted to organize maybe a visit to the High Performance Supercomputing Center in Puebla, so that you could visit and see the racks and see the processes, and that they explain which are the kind of processes that they are running. So if at the end this is not possible, what I will do is I will try to have a connection in Barcelona where I have worked to see whether even in distance you can see the applications. Other questions? Yes, please.
Thank you. Could you please repeat? I know that we set the Java home environment, but I wanted to ask, why was that? Is Hadoop? Does
Because
Hadoop
you can program in many different languages on top of Hadoop. You can use Python, Smalltalk, C, C++, Java, Scala, many different languages. I need to understand. So with for example, us in the exercise with the same environment, the first exercise is done in Java, and the second will be done in Python. I need to understand.
Very well. Thank you, Dr.
And so for Java, it's like normal use of Java where we have to set the path in order to run our programs. Other questions? If there are no further questions, I'm going to close the session here. We will meet next Friday for more algorithms and other discussions. And just let me see, you have the assignments. The second round, did I have another assignment? Yeah. Yes. So the assignment that so that you can complete the this exercise. Well, the exercise is due to the next lab. So in the meantime, please ask on Slack or in any media that you prefer if you have questions. And you are challenging 5 points. Okay, so I wish you a nice, what is it, during the day, a nice day. And we will meet on Friday. Okay. Yes, have a great week. We are starting the week, well, more or less Tuesday, but it's true that we're starting.